Hello biotech scholars, welcome to a video that is going to model for you how to do steps 7 and 8 of the scientific method. That is basic results analysis and drawing conclusions from those results. This is also directly applicable when you are doing a data analysis CER, because that's really what a data analysis CER is. You take a data set someone else has experimented to find and you do the rest of the scientific work from that point. Now, I want to be very clear in where it is best to use this, not only in our academy, but moving forward through your academic life. This model is a good basic model if you are instructed to write conclusions and you are given no other guidance on how to do it. If a professor or other teacher gives you a specific template of I want you to do X, Y, and Z, please do their X, Y, and Z. This is meant to be a good training wheels. You're given no guidance. I don't know what I'm doing. I'm just starting out. I'm not actually an expert in this, so I don't know how to do the statistical analysis. This is basically your advanced science literacy toolkit for non-scientific experts. So let's dig right into it. Here is the scenario that I'm going to model for you today. So what we're assuming is we have discovered in phase 4 clinical trials. Now remember, those aren't a real phase of clinical trials. That's when the drug is already approved by the FDA. It's being sold to the general population, but we are monitoring the general population's use. So we've discovered in phase 4 clinical trials that patients with genetic condition X, that's all we're going to call it, have worse side effects from a cholesterol pill than the general population. We have decided to run additional trials to determine if a lower dosage is more efficacious for patients with condition X. In particular, we are looking to see if the dosage produces less side effects while still lowering cholesterol enough to be worth it. This right here, this is our big question. Now we would have to turn this into a scientific question, which I'm not modeling for you in this video, but this is our big prompt that we would have designed our research around. When we designed our research, we had 3 groups, and we had 3 trials per group. Now that would specifically mean 3 patients. Our dependent variable was the amount of cholesterol in millimoles per liter, and our independent variable, the thing we are altering to figure this out, is the dosage. Now, just to do some experimental design review, the 0 milligrams and the 12 milligrams would be what we would actually consider control groups. This would be considered the positive, good thing these erase. The 0 milligrams would be the negative control because that represents what is normal. Like, this is a patient who has high cholesterol and they're taking nothing for it. So the negative control represents the normal. That's what we are not going to change or add anything to. In drug trials, this is also referred to as the placebo group. Although that term is just a drug trials term, we don't call the negative control a placebo in non-drug trial scientific research. Then the 12 milligrams would be the positive control, because that is the current dosage. So we know for a fact that this 12 milligrams lowers cholesterol. That is why it's the positive control. We know it will produce the results we want. That therefore makes the 5 milligrams the experimental group. So we are looking to see if we are investigating if this dosage will address our issue that we have here. So you can see that this data table just covers one aspect of what we're looking at, which is does it still lower cholesterol? Now, I'm assuming that I am a researcher who has been presented this data set. Maybe I didn't actually gather this data from the clinical trials, but this has been sent to me and I have been asked to analyze this data to address this core issue. This would be my first step. Step 1 is I would do a scatter plot of the data. So so this is an appropriate graph based off the graphing lesson. This includes all appropriate 7 steps of a perfect scientific graph. I have used multiple colors. Now, a scatter plot is where you just graph each individual point. And the reason why I'm starting with a scatter plot, I'm going to do this in Sharpie. Why did I do this first? Why first? Because this is going to give me a big picture view of outliers and trends. So basically, by seeing where my data clusters, let me actually redo this color so it shows up better on film. So I'm going to do this in red. So the red data points are my 12 milligrams, my positive control. The blue data points, which are clustered up here, are my negative control, and these green data points are my experimental group. Now, the reason why this dot is larger than all the other dots is because we had multiple data points that were the exact same. So in a scatter plot, if you have multiple points that are graphed at the same point on the graph, you make the point larger each time you have an additional dot, just to show, hey, we have a lot of data here. So when I'm looking at overall trends, it does appear as though we have the higher the dosage of the drug, the lower the cholesterol, even this experimental dosage we're looking at. And in this group, it looks as though we have a nice little cluster of data. It doesn't look like we have outliers in our negative control. Same thing in our positive control group. However, when I look at our experimental group, I have one point that's way down here. And so I'm already wondering to myself, is this an outlier? But to be clear, you actually just can't eyeball an outlier, although that is kind of the general purpose of doing a scatter plot. It's a quick and graph to give you big picture ideas and let you know what further statistical analysis you need to do. So there's our scatter plot. Now, the thing I'm going to do next is I'm going to come back to my original data set, and I'm going to do the math to calculate the 3 M's: the mean, the mode, and the median. So I'm going to do that here for each of my 3 groups. This is the 0 milligrams, the 5 milligrams, and the 12 milligrams. So to calculate the mean, of the 0 milligrams, you would add those up and divide by 3. When we do that, I get 166.6 repeating. I'll put that in my data table because I've now calculated that. The mode, for this one, there is no mode because every number only appears once. The median is the middle number. When I sequence these, it goes 160, 168, 172, so the median is 168. Now, what I'm going to do before I move on is I'm going to start looking at this data. And I see that I'm not going to really look at mode because I don't have one, but you would compare the median and the mode to the mean. If the median and the mode are close to the mean, that means it's unlikely you have an outlier. So I've got 168 and 166.7. So I'm going to write down my initial idea where that outliers are unlikely in this group. Then I'm going to repeat that process for my experimental group. The mean for this is 137.3 repeating. I got that by adding my 3 data points and by dividing them by 3. I will add that mean to the data table. My mode, well, I see I have 2 numbers that are the same, so that is my mode, 152. And my median, again, when I put them in order, 108, 152, 152. My median is again 152. So now I'm going to compare my median and my mode to my mean, looking for outliers. Well, my mode and my median are in very nice agreement with each other. However, that could be a pretty significant difference. We're looking at about a 15-point difference between the mode and the median and the mean. And because the mean is lower than the mode and the median, that means our outlier would be pulling down the average. So if the mean is lower than these, the outlier is pulling it down. If the mean is higher, the outlier is pulling it up. So I'm just going to make a quick note about, do we have a low outlier? That a low outlier is possible. So I may have a messed up data set. And then when I look at my original data set, I see that I do have this 108. On first look, that looks like it might be an outlier, but again, we cannot just eyeball outliers. We have to do statistical analysis to find them. So then that brings me to my final group, where I will repeat the 3 M's, the mean, the mode, and the median. And the mean for my 12 milligrams, that is my positive control, because that's the current dosage that we know works. My mean is 140. Oh, look at that. My mode is NA, because I don't have any repeating numbers. I will also put in my mean in the graph, because I've now calculated it. And my median, when I sequence my numbers, 138, 140, 142. My middle number is 140. Well, looky there. My median and my mode, my median and my mean are exactly the same. So it looks like outliers in this group are also unlikely. Now, before I do any further graphing, what I'm going to do now is I am going to figure out if this group has an outlier like I suspect. And to do that, I'm going to use the process of calculating standard deviation. Now, to be clear, if I were actually a researcher and this was my job and my primary investigator said analyze this data, I would in fact calculate standard deviation for all of these. But for the sake of time of this video, and after I've done my initial kind of big picture, I've looked at my scatter plot, it looks like I might have an outlier here. When I do the 3 M's, they confirm I might have an outlier in my experimental group. For the sake of time, I will just be calculating standard deviation for this group. So to do that, it's a 4-step process. Step 1, you calculate the mean, which I've actually already done. So the mean was 137.3 repeating. And then step 2, I need to calculate the variance. And to calculate the variance, you take the data point, each data point, so there's 152. You subtract the mean, and then you do it to the second power. I've already pre-calculated this. I'm not just a mental math whiz. You know quite the opposite if you've had me as your math teacher for a while. And then I will repeat this with the next data point. Oh, hey, very helpfully, it's the exact same calculation, because the exact same number appears twice, but I would still calculate it twice for the variance. You calculate it every time the number appears. And then last but not least, I take my last data point, 108. Whoops, 108. I subtract the mean. Then I square it. And I get 858.49. Step 3, I will then add together these 3 variances. Nope, you copied that wrong, Barker. 858.49. I will do that in the calculator now. Okay, then I will divide that, because this is a sample, so this is not the full population. I will do n minus 1, which would be 3 minus 1, because I had 3 members of my sample. Whoops, 3 minus 1, which would be equal to 2. So I'm now going to divide this by 2, which gives me this number here, 645.335. And then I will do the final step of calculating standard deviation, where I will take the square root of that number, which I will do right now. Second, 645.335, close parentheses. Now, this gives me this long number, and I'm going to actually model for you using appropriate number of sig figs. So when I look at this, because this is multiplication and slash division, I see I have 6 sig figs here. So I will go to 6 sig figs here. Yes, 1, 2, 3, 4, 5, 6. That would be my rounding line. I look behind it, that's a 4, so I'll round down. So my answer is going to be 25.4034. That is my standard deviation for my experimental group for the 5 milligrams. I'm going to take this and set it aside, because now I am going to flip this paper over, and I am going to do a quick little bell curve graph of this. So in a bell curve, you would graph your mean, which, as a reminder, my mean for this group was 137.5. So I know that's the peak of my bell curve. I would then take my standard deviation, which was 25.0434, right? And I would figure out my first range of 1 standard deviation. So this is 1 standard deviation. To do that, I take my mean, 137 point, oh, no, it was actually 0.3 repeating. I put 0.5. Whoopsie. There we go. Subtract the standard deviation. And that gives me 111.89. Actually, if I'm doing sig figs, this is a subtraction, so that would be to the least number of decimals. The least number of decimals is 1, so that would be 111.9 as my lower range. And then I would take 137.3, and I would add my 1 standard deviation, which was 25.4034. And that means that this is 162.7, because I just have 1 decimal, and so I'm rounding to the least number of decimals to get the right number of sig figs. So that means any data points between 111.9 and 162.7 are within 1 standard deviation. That means they're definitely not outliers. So now I'm going to come back to my data set, and my 152 and my 152, they're in this range. That means I know these are good numbers. Even by the strictest scientific analysis or statistical analysis, if you are within 1 standard deviation, that's a good data point. Now, here's where it can get a little messy. Science oftentimes cuts it off at 1 standard deviation, and they say, that's it. That is what is acceptable outliers. But if you go to Khan Academy videos, you read statistical textbooks, which I have done when I was teaching myself this, they will say that 3 standard deviations is the cutoff point for an outlier. And from what I can tell, that is basically like the largest range you could ever give yourself. But because science is usually times a lot more specific, you would, like, and I mean hard sciences like chemistry, biology, physics, you would cut yourself off at 1 standard deviation. Now, let's just play for a second. Let's pretend we're soft science, like, oh, who am I going to come for today? Psychology and sociology. So let's say you're a psychologist or a sociologist, and you're a soft science, which means your data is a squidgier than the hard sciences. So we're going to do 3 standard deviations. That means I would take my standard deviation, 25.4034. Well, actually, I would take my mean, 137.3 minus, and then I would subtract this 4 times. You could, or 3 times, excuse me, because we're doing 3 standard deviations. You could certainly multiply your standard deviation by 3 and then just subtract that number. The math will work out the same either way. So, if we were going to go to 3 standard deviations, and that's what we were going to set our outliers by, then our lowest acceptable point would be a 61.0898. And our highest point means I would have to add the standard deviation 3 times to the mean, 137.3, so I'll do that right now, 25.4034 plus 25.4034 plus 25.4034. And that gives me 213.5102. So, if we were going to use 3 standard deviations as our cutoff point for outliers, well then, this 108 is still definitely within that range. It is clearly between 61 and 213. That would mean if we were using 3 standard deviations, we would keep all of these numbers in. Now, what you would do next is, when you have figured out what you're going to do, are you going to go by 1 standard deviation, 2 standards, 3 standard deviations, 1.5 standard deviations? And usually you would just listen to your PI and do what they tell you to do. You would graph it. Now again, this is a perfect graph using the 7 steps I've told you to look for. This is what it looks like when we're using 2 standard deviations, meaning you don't cut out. This is what it looks like when we're using, 3 standard deviations. So we would not cut out this outlier. That's actually not an outlier. According to 3 standard deviations, that's a valid data point. So we are just going to graph these 3 averages. And so when I do that, this is the trend line I get for what we're seeing. And when we leave this guy in, it actually looks like the 5 milligram dosage is more effective than the 12 milligram dosage. Now here is what the graph looks like when I'm only using 1 standard deviation. To do that, you go back in, you get rid of the outlier because 108 is not within 1 standard deviation. So goodbye, so long, farewell, I'll be to saying good night. And then you would recalculate your mean based off of what you've left in. I don't really have to do that because it's just 152 because it's the same number twice. So my new mean when I exclude that outlier is 152. And when I graph that, hello, we have a very clear trend line which shows that the 5 milligram dosage does lower the cholesterol, but it is not as good as the 12 milligram dosage. So I'm just going to show you those 2 side by side. This is where standard deviations really, really matters. These are 2 very different graphs that show you very different conclusions. When we have a very wide standard deviation, meaning 3, we don't get rid of anybody, and it actually looks like 5 milligrams is the most effective dosage. But when we get rid of that outlier, because we're only using 1 standard deviation and recalculate our mean, it is clear to us that though 5 milligrams is better than nothing, it is not as good as 12 milligrams. This is why a really excellent question, a science literacy question, to ask someone who is giving you facts, or they're saying, hey, these are facts, you actually don't know if they're facts, is what standard deviation did you use? And if it is anything greater than 1.5 standard deviation, you should really question the validity of that research, because a 3 standard deviation would give a completely different set of facts than a true 1 standard deviation or 1.5 standard deviation would. So sometimes that's a way scientists can try to create fraud without actually creating fraud. They're just like, oh, I'm going to allow 3 standard deviations. Okay, I'm looking at this video. So what I'm actually going to do is we are going to do 2 videos because Lord knows that was actually a lot. So what I'm doing on the fly is this video actually just covers how to model basic results analysis, step 7. I will film another video for how you use those results to draw your conclusions.